My name is Qingkun Bao. Today I am going to briefly introduce Abacus, precise SetChannel Analysis. Suppose we have a program. It takes some sensitive information as the input and outputs the result. The process can be applied to many programs like the encryption, decryption, and data processing procedure. However, during the computation, an attacker may have some observations like the sound, the execution time, and the power consumption. If an attacker can infer part of the original information based on those observations, then we call it a SetChannel attack. Modern computers use the virtual memory. It allows multi-processes share the same physical memory. It often happens when multiple applications use the same dynamic libraries. Here is an example. When a victim program accesses the data at virtual address 3 from the memory, the CPU reads the data from the main memory and the cache stores a copy of the data. Next, when an attacker program accesses the data at virtual address 3, because the cache has the data, then there is no need to read data from the main memory again, so the access time is fast. However, if an attacker accesses the data at virtual address 5, then the access time is slow because the data is not in the cache. So by measuring the timing to access the data at different addresses, an attacker can infer an address that the victim just accessed. The key intuition of many SetChannel attacks is that many SetChannel attacks happens when the program accesses different data or code for different secret inputs. We call those attacks address-based SetChannel attacks. There are two kinds of patterns shown in the slide. The first type is called secret-dependent control flow transfers. K is the sensitive input and its value passed into a temporary value. Depending on the value of the temporary value, the code may execute branch 0 or branch 1. The second type is called secret-dependent data access. An index is calculated based on the secret data. T is an array and the code uses the index to access the array, which may also result in access different memory locations. This is our work, Abacus. It can identify and quantify SetChannel leakages in real-world applications. We use symbolic analysis to capture the dependency between the observation and the original secrets data with math formulas, and quantify the amount of leak information defined by the reduction of the search space. For the detection part, our tool is faster than all the previous tools while identify all the known leakages. For the quantification part, our tool can automatically find severe leakage sites. The leak information is represented with the orange color in the slide. Let's look at a concrete example. Before an attack, the key variables could be any value from 0 to 255, so the size of the initial search space is 256. If an attacker observes the code of execute branch 0, then the remaining key could be any value between 0 to 7, and the remaining search space is 8. The information leakage is equal to the size of the initial search space minus the remaining search space. In this example, the observation can leak 5 bits of the original secret information. Here is the overview of Abacus. It takes a binary executable as the input. After that, we run the binary and record the execution trees. Next, we run the symbolic analysis of the execution trees and construct formulas that represent each potential leakage site. Finally, we run the Monte Carlo sampling to estimate the remaining search space and get the amount of leaked information. In this example, leakage B leaks more information than leakage A because the remaining search space of leakage B is smaller than the remaining search space of leakage A. The first step of Abacus is to record the exclusion trees. We mark the secrets data manually. It can be done by adding the annotation on the source code or telling the addresses of the secrets in the binary code. We run the binary executable under the dynamic binary instrumentation tool and record the execution trees. The execution trees consist of the runtime information, including the OPC code, operand, register value, and the memory access information. Next, we run the symbolic analysis on the machine instruction directly to capture the relationship between the original secret input and the attacker's observations. We only treat the secrets as symbols. For other data, we use concrete value. If all the operands of one instruction are concrete values, we do the concrete calculation. Otherwise, we do the symbolic calculation and the concrete calculation. In this example, we capture a potential secret-dependent control flow leakages by constructing a formula with the zero flag and carry flag. In many situations, the size of the initial search space is known, so the problem is to quantify the size of the remaining search space. It is a problem called model counting. There are two kinds of model counting. The first kind of model counting is called the exact model counting. Exact model counting is slow and not scalable. In our project, we use a proxy model counting. There are two challenges. The first one is that the curse of dimension problem, and the second one is that the number of satisfying assignments could be very small. We use two heuristic techniques to mitigate the problem. If you are interested, please refer to the original paper. After that, we give the error bound with the Central Limit Theorem. Abacus is implemented in C++. The trace collection is implemented as an Intel Pin tool. The symbolic analysis engine is implemented from scratch. It can handle 8088 integer instructions. We also implemented the data flow analysis. It can provide the call size from the original secret input to the actual leakage site. The debug information parser is implemented to give a fine-grained information such as the line numbers and the file name of each leakage site to help developers to identify the leakages in the source code. We evaluate Abacus on real-world application. The evaluation results show that for the detection part, our tool is faster than all the dynamic tools. We do not find any false positive. The tool can identify all the leakage sites identified by the previous tools. For the quantification part, Abacus provides valid estimations for the leakage site. Most severe leakages are patched in the later version. Here is a case study for the RSA implementation in OpenSSL. We quantify all the leakage sites in OpenSSL in different versions and compare the result with the changelog. The results show that new versions of OpenSSL leaks less amount of information compared to the previous versions. In our evaluation, we find all the leakage sites that leak more than 6 bits of information are fixed in the later version. We quote the update from the changelog. OpenSSL developer has adopted several methods to mitigate side-channel leakages. With our tool, we find that most severe side-channel leakages are patched in recent OpenSSL versions. In conclusion, Abacus is a tool for precise side-channel analysis. It has two components, detection and quantification. The prototype is open source. In addition, we open everything, including source code, the benchmark, and raw result. The two-part artifact evaluation, and we receive a reduced budget.
Hello again. We are here with the author. My poor eyes. Uh,
Mm,
Queen Kung. My
mm.
poor eyes don't read the small letters in the screen. And we are eager to answer your questions. Queen Kung, it's when you work in this side channel attacks, leakage things, it's like magic to me. This is really impressive. You look at computer and touching the computer or listening to the sound or doing things like those, you know what's happening inside. It's really impressive. It's something that I'm not used to understand.
Okay.
Can you summarize briefly the main contributions of your work? I mean, what you have, your proposal. What is it useful for?
Okay, I think the contribution in my project is that actually there are tons of papers on the side channel detections. So basically, you have a library, you have a tool that you can detect plenty of side channel leakages. And the problem with previous tool is that no tool can provide an estimation to access the side channel leakage site because probably you can have like 100 side channel leakages but you do not have a tool to tell you which leakage is severe. So my contribution in my project is that I thought we somehow provide a method that in the information theory to give an estimate and to quantify the amount of leakages. And even more, so our tool, works on the real world software like OpenSSL and BTLS and identify some severe section no leakages.
But I should not worry that you are going to steal my information right now. I
Mm,
imagine. So my computer is safe with your proposal.
yeah.
You will not steal my credit card number or anything with it, isn't it?
Yes.
Sorry about that. You have a question in the chat. Rashmi has made
Mm,
it. Can you see it?
yes, I saw the question. Yeah, I can answer that. Yeah. And yeah, the first question is that did I evaluate my tool on the latest version of SSL? And the answer is yes. And we evaluate the latest version of SSL 1.1.1. And we actually identify some side channel leakages, and the developer has addressed them.
And
And
there is a follow-up question by the same.
yeah, yes, and uh, the second question is actually we actually did a case study that about OpenSSL, and we compare multi versions of OpenSSL, and we found that the two that the leakage side that leak more information, like say several more bits are all fixed by in the latest version in OpenSSL.
The empirical evaluation that you made makes clear that your proposal is able to identify the number of bits, the information that is leaked, and the other way around. Can you let's say feedback, get information from your proposal to improve the code? I mean, uh, how can we what can we do as programmers to improve our code based on the findings that you have about leakage?
Sorry, I didn't get your question.
No, what I mean is, if I have a program that leaks information, I need to fix it. You give me an amount, a measurement of the information leaked. Can I use that information from a practical viewpoint to make my product more robust?
Oh, okay. I think it depends, and it depends because we quantify the information basically with the information theory, but you can understand in intuition way. Suppose you have like password checker, and the password checker take like of 8 bits of secret key, so the initial search space is 2 to the power of 8, right? It's 128 possible keys. And you have side channel leakages. And if our tool report that the leakage leak, like say 8 bits, like say 4 bits. So what does it mean? It means that right now the search space is only, let's say, 60, like it's only is 8 because to the power of 8 minus to power the 5 equal it is 2 to the power of 4. So it's still it means that right now the search space is much smaller than the initial search space. I would recommend. Sorry, I would.
No, it's fine. It's fine. I remember that the traces that you get are obtained from from the object code.
Mm,
And what I don't remember if you have to do some manual labeling on the code.
Uh, yeah. The manual process that you have to tell the tool so which data is the secret.
Mhm,
Because not always the input is the secret. For example, the public key is not the secret, but the private key is the secret.
mhm,
So it can be done to mark the information on the source code. It's basically similar to some, tint analysis tool you have to tell. So this secret or some symbolic tool, this secret is a symbolic, something like that.
mhm.
And after that, the tool will only, trace the secret. It,
It's interesting because it gives a lot of flexibility. You don't need to have the source code of an application to analyze the program. You only need well, knowledge of the secret data, and that's it. Once you have the object, it will be enough for making the analysis, isn't it?
Yes, and also I want to say that we have released basically everything, include the source code, the benchmark, and the raw evaluation result. So we also provide some script, and we all the data, the source code, it can be found on the GitHub website. And so if everyone who is interested in the tool, you can download it and try it. If you have questions, you can post issues on the GitHub pages, so I can probably kind of help you find the problem. So that's the project.
Anyhow, regardless, or in addition to the community being able to test the tool, it looks a so finished product that it can proceed to industry with little adaptation. Do you have any contact with industry, with potential I don't know, people that may apply this in practice in real products in the market?
Uh, so sorry, I don't think this tool is ready for production. Yeah, but I that's my planning is to like contact the two actually. So I'm going to finish my PhD and I'm going to join a company. We have a crypto library and actually I'm going to apply the tool, on our future product. Yeah, yeah, but I don't have nobody in the industry has applied this tool yet.
And about future lines, do you plan to stay to keep on doing research on this direction, or do you see lines of improvement or something?
Yeah, I hope so. It depends on the feedback. If the tool become popular, yeah, of course, I hope I can, you know, improve the tool and probably make this into a product.
Do you plan to make a product out of this? That's interesting.
Okay, okay.
That's interesting. That's really interesting. Well, and what else? Is it something I mean, this is a paper. You know what the papers are. They only reflect a situation in time. Do you have something that is there any side of the problem that you wanted to analyze in this tool, but you couldn't, and you still have it pending for the future?
Yes, I'm planning to evaluate the tool on some machine learning library and some media library because uh, attackers are becoming popular to attack the SetChannel leakage, not just in crypto library. The problem with the current tool is that it cannot handle the floating point instructions.
Okay.
Okay, yeah, that's one of the limitation, but yeah, we're hopeful to address the problem in the future.
Sure, there will be. Well, gentlemen, ladies, it's almost done. So I encourage you to join us in the discussion.